In this video, we are going to discuss about the need for biasing. On the completion of this biasing, the students will be able to provide the comprehensive understanding of this electronic devices and the circuits, and also they can understand the working diagram of the transistor. So in the case of the need for biasing, why we are going for the biasing technique? So we need the stabilized, that is to make the amplifier to amplify in a linearly, that is to get a linear amplified signal. Here we need a biasing technique, that is this biasing establishes the DC operating point for the linear amplification. So if this amplifier is not biased in a proper way, means this DC voltages on the input and the output can go to the saturation mode or it can go to the cutoff mode, so that whenever an input signal if you are applying to that, there will not be any proper amplification. If that it can obtain a half, that it can goes to the saturation mode or it can goes to the cutoff region. So in this part, output signal, if it is amplified in this in the case of the input signal, if it is inverted, this means it can be a phase shift of 180-degree phase shift, so that the output signal signals equally above and below the DC bias signal of output. So here if you see this need for biasing, you can see the nonlinear operation in case of cutoff and also in the case of saturation region. So if it goes to the cutoff region, there will be a cutoff in the positive side, and if it goes to the saturation region, means there will be as a cutoff in the negative side. So here improper biasing which causes distortions in the output signal. So you can see the positive portion of output positive output voltages cut off in the case of the cutoff region, and the saturation region you can see the negative cutoff. There will be a negative distortion, so that there will not be any proper amplification in the signal. So due to these cases, we are going for the need for biasing. So this biasing, this is one of the application of the DC voltage which we are establishing to provide the fixed level of current and as well as voltage. So this transistor amplifier, if we are considering the transistor amplifiers, means this resulting DC current as well as this voltage establishes a proper operating point, that we can say that it can implicate for the proper amplification. Also, if this operating point is fixed, means then we call that point as Q point. So this operating point is also, we call it as bias point, or we can call it as Q point, or this output characteristics which shows that the DC emitter voltage as well as the collector current with no input signal. So you can see the fixed bias circuit. So if we are applying the KVL along the input side as well as the output side, first we are applying the KVL along the output side, so we get that IC is equal to VCC minus VCE divided by RC, so that we get it as 1 minus 1 divided by RC into VCE plus VCC RC. And in the case, you can see the diagram of the saturation region, cutoff region, and also the active region. So we need the transistor to amplify in this active region, so that we have to point out this Q point, that we have to get the stabilized output, so that we may get the proper linear amplification. So in the case of the saturation point, here the point at which we can say that the load interacts with the characteristic curve near the collector point. Near this collector point, we call that as saturation region, and also this point, that is current which is flowing through this transistor, will be maximum and the voltage will be minimum. So that this saturation current for the fixed bias, we can say it as IC saturation is equal to VCC by RC. And in the case of the cutoff point, so cutoff point, we can say that the point where this line interacts near the cutoff region, that is collector curve is referred as the cutoff point, so that it will be the end of the load line. So at this point, we can say that collector point is approximately 0, or the emitter is grounded. So we say that VC is equal to VC equal to operating, then VCC operating point, that we call it as Q point. So we know that Q point is nothing but the operating point. There will be no input signals can amplify. And in the case of case 1, case 2, case 3, there are if this Q point is placed at a point P which is near to the saturation region, then there will be a clip off for the positive region, so that the distortion will be present in the output and it is not suitable for the operating point. And the case of case 2, if you are seeing, means that is, if it is biasing point, that is Q point which we are saying is placed near the point of R, means then that is near to the cutoff region, so there will be a negative clip off, so which is also not suitable for the operating point. And in the case of case 3, this biasing point which is present in the q point is q is near to q point, then it is, we are saying there will be a sinusoidal waveform without any distortion, and we call that as a q point, which is a best